Now I want to talk about ionic bonding. I know you learned a lot of this last year in biology, so try to remember this as we go along. Remember that ionic bonds take place between a metal and a nonmetal. There are other variations on this, but for right now, let's stick between a metal and a nonmetal. And if you think about the trends, the periodic trends that we just talked about, in order to have an ionic bond, you have a large difference in electronegativity between the two atoms in the bond. We'll talk more about this as we go through this chapter. Now, if you'll recall, if I have, let's say, lithium, here's lithium, 3+ nucleus, 1, 2 electrons inner shell, 1 electron in the outer shell, lithium. Let's say I have fluorine over here. Fluorine has 9 positives here. It has 1, 2 electrons here. It has 1, 2, 3, 4, 5, 6, 7 electrons here. Now, it's actually a big pain to write these things for every element, so we're going to do a shortcut. We're going to do what's called Lewis dot structures. I'm pretty sure you did these last year in biology. In Lewis dot structures, we're going to use dots to represent electrons. And the only electrons we are going to do are the valence electrons. The valence electrons. Remember what valence means? Valence means the outermost. S and P electrons. D's and F's don't count. Those count as inner shells. Okay? So if we go back here to this page, I've got lithium here. Now, the inner shell are these 2 electrons. We don't care about them. The one has 2 electrons. All we care about is this outer shell electron. So I'm just going to put 1 dot right there. Here's my F. Again, I don't care about these 2 inner shell electrons. I only care about these outermost ones. There are 1, 2, 3, 4, 5, 6, 7 of those. 1, 2, 3, 4, 5, 6, 7 electrons. Now, you'll recall my mantra, which is everybody wants to be a noble gas. What I mean by that is every element reacts, its motivation for reacting is to be lowest in energy. And it's lowest in energy when it has a filled shell, like the noble gases do. So lithium can get a filled shell, be like helium with its 2 inner electrons here, by losing this one. Fluorine has 7 electrons. It wants 8. So it can have a filled shell by gaining an electron. So lithium loses its electron. Fluorine picks it up. So remember, an ionic bond, there's no sharing of electrons here. This is a kidnapping, a snatch and run mission. This electron here that was over in lithium has left lithium permanently and gone to fluorine. So now I have ions, hence ionic bonding. I have a positive ion, that is the lithium, and I have a negative ion, that is the fluorine. You'll notice this positive and this negative mean positive 1 and negative 1. Chemists never write 1s if they can help it. If it's not a 1, then you have to write the number. But if it is a 1, people tend to leave the 1 off. As long as we are talking about these things, let me give you some definitions. A positive ion is called a cation. Okay, cation, C-A-T-I-O-N. That's the name for a positive ion. It's not pronounced cation. It's pronounced cation because it comes from an electrochemistry word called the cathode. Anion, A-N-I-O-N, these are all one word. That's a negative ion. And that is again pronounced anion, not anion, because it comes from the anode of an electrochemical cell. So, an ionic bond, officially, is the electrostatic attraction between positive and negative ions, between cations and anions. Okay? So electrons are being transferred, creating ions, cations and anions, and then those cations and anions attract each other, as positives and negatives do. And that is what we call an ionic bond. All right, let's do some more examples. Let's say I have Mg and F. How many valence does magnesium have? Look on the periodic table. You'll notice it has 2 electrons, 2 valence electrons. Fluorine, once again, has 7. So let me do what I did before. I'm going to take the 1 electron and move it over so that fluorine's filled. Oh, but look, magnesium is not filled. It still has 1 electron. I can't have that. Okay? I can't have magnesium with 1 electron. That doesn't give it a noble gas configuration. I need it to have a noble gas configuration. Okay, so what should I do? Well, the answer is I'm just going to write down another F with its 7 electrons. I can write down as many atoms of either magnesium or fluorine as I want, because remember, I never have just one. Think about a mole. I have bazillions upon bazillions of atoms if I have anything I can deal with. So I'm just going to write down as many as I need. So this other F can get this other electron. Now magnesium has a filled shell. It's a 2+ ion. You can write 2+ or +2. I don't make that distinction. And then I have 2 fluorines. Both of which have filled shells. Both of which are negatively charged. So you'll notice I have the same number of positives as I do negatives. 2 positive, 2 negatives. The positives plus the negatives have to equal 0. There has to be the same number of positives as there are negatives. And if you move the electrons, so that the anions are filled and the cations are filled, have filled shells, you'll always get the right amount of charges. Let me give you a hard one to do. Aluminum and oxygen. So the first thing I'm going to ask you to do is write the valence for those two things. Okay, here's the valence. Aluminum has 3. Oxygen has 6. Now what I want you to do is make me a nice ionic compound using these Lewis dots and this movement of electrons, just like I've shown you, to show me the aluminum cations and the oxygen anions that make a neutral compound. All right, let's see what you did there. Well, first, my oxygen needs 2. So I'm going to move 2 over. That makes oxygen happy. But I still have 1 electron left. So I'm going to write another oxygen. And I'm going to take this electron and I'm going to move it over here. All right, now the aluminum's happy, but the oxygen's not, because the oxygen still needs 1 more. Okay, I'm going to write another aluminum with its 3 electrons. I'm going to take 1 of those electrons and I'm going to move it over there. That makes that oxygen happy. But I still have these 2 electrons on aluminum, so I'm going to write a 3rd oxygen. And then I can move these 2 electrons right there. And finally, at last, everybody's happy. Let me write this out clearer. I have 2 aluminum 3 pluses. And I have 3 filled shell oxygens. These guys are all 2 minus. So look, I have 6 positives total and 6 negatives total. So again, it's neutral. And that's exactly what I want. Now, if we think about this, just like we did the metallic, if we think about this in terms of macroscopic properties, what are macroscopic properties of ionic compounds? Well, one of the things is just like the metallic bonds, we have high melting and boiling points. Metallic's a little stronger than ionic, but still high melting and boiling points as compared to covalent. And this is because that electrostatic attraction is very strong. It's hard to break it. Ionic things do not come as, say, 1 lithium and 1 fluoride put together. I mean, we just drew Li plus F minus as if those were the only ones in the beaker. But in fact, ionic compounds come as what's called a lattice. I have a model in the lab. I'll show you. But a lattice really is this. If the purple ones are the lithium and the red ones are the fluorine, essentially you've got a whole bunch of them all surrounded by each other. Remember, this is a 3D picture. This fluorine here not only has 4 lithiums around it, but it has 1 that's between you and the fluorine and 1 that's in the back of the computer. So it's literally surrounded by 6. And so are all of these red ones. So they're very stable and they're very happy. So it's very hard to break these electrostatic attractions. So high melting and boiling points. The other thing we can say about these things is they tend to dissolve in water. They tend to dissolve in water. That's not true of all of them. I can tell you lots of ionic compounds that do not dissolve in water, and I'm sure you can think of some too. But in fact, most ionic things, to some extent, dissolve in water. Now, why they do that is because water stabilizes the ions. Think about water. Water looks like this. Again, I'm sure you heard this in biology. Water looks like this, and it's polar. We're going to talk more about this in a later video. But this end of the molecule is sort of kind of negative, and this end of the molecule is sort of kind of positive. That's what this funky symbol means. It means a partial charge. Water is not ionic. Water is covalent. But it's very, very polar. There's a sort of kind of negative end and a sort of kind of positive end. So when ionic things dissolve, I have lithium plus, the water is going to surround the lithium so that the partial negative end of the water is oriented toward the lithium. Here's my F minus. Water's going to surround it too, but you'll notice the other way. So the H's are near the F. Because that's the partial positive end of the molecule. But what it does, this is called solvation. Solvation. And it stabilizes the ions. So that's why ionic things tend to dissolve. Because the very polar water can stabilize the charges. The other macroscopic property I want to talk about here is when dissolved in water, ionic compounds, or rather solutions of ionic compounds because they're dissolved in water, will conduct electricity. Remember what I said in the metallic video, the metallic bonding video, that in order to conduct electricity, you need moving charges. Well, if you have a lattice, a solid, you've got charges, but they aren't moving. But you have this, you have the ions dissolved in water, now you have ions that are free to move. So that's why ionic compounds will conduct electricity. So that's all we're going to talk about with ionic for now. Covalent comes up next in another video.